Good morning. I am Joe Kovacic, and I work in the DISA Emerging Technology Directorate. We would like to welcome you to today's technical exchange meeting. MEM Computing will be presenting its prime factorization solution in today's session. Need to go over some administrative items before we get started. First, please mute your DoD 365 joint Microsoft Teams sessions. Second, this session is being recorded to allow future scrutiny of the presented capability by members of DISA and the DoD community. Third, this is a public forum, so no proprietary or sensitive information should be shared in this session. Fourth, we encourage questions during the session, so please use the raise hand function in the Teams menu to alert the presenters when you have a question. You can also enter your questions in the chat area anytime during the presentation. Questions will be addressed in the order they are received. I must provide the following disclaimer. This technical exchange meeting does not infer any intention by DISA or the Department of Defense to enter into an acquisition, contract, purchase, or endorsement of the presented capability. This session is purely for informational purposes only. We do not control how session participants will proceed with the conveyed content. Access to the technical exchange video, slide deck, and other artifacts will be made available through the Open Hive collaboration website, whose link is provided in the TEM session invitations each of you received. I also provided a link to the slide deck to access the slide deck in the chat area. I'll repost it again there shortly. And with all that said, let us commence with the presentation. So over to you, MEM Computing.
Okay, thank you very much. I assume someone will let me know if the sound has any issue. So thank you. Thank you everyone for being here. My name is Tristan Sharp. I am a principal scientist at MIM Computing Incorporated. So I get to introduce some of our work to you today. We at MIM Computing are developing and commercializing a new compute architecture. And that technology is called MIM Computing, and it's where the company gets its name. So the primary applications that we work on are combinatorial optimization and certain edge compute applications. So I'll describe those areas and the services we offer. And that's the part essentially about the company for this DISA TEM talk. And then I'll also get to describe some of the recent results from a project we did where we applied our approach to the problem of prime factorization. So first, like I said, I'll give some background on MIM Computing, both the technology and the company. And then start kind of the second half of the talk. We'll have to get a little bit technical to really understand and interpret the factorization results. And then I'll describe the circuit design that we have for factorization as part of a SBIR project that we did. Provide the results, and at the end, hopefully be able to demo our MEMCPU platform. So first about the company, we leverage patents related to next generation compute architectures. That's primarily for combinatorial optimization and edge compute applications. Originally, the founders were doing academic research on unconventional computing at the University of California, San Diego, and spun this off into the company in 2016, and we're still located in the San Diego area. And we've done work with government, industry, and academia. So, yeah. So we are part of it's kind of an emerging field of development in unconventional compute architectures, essentially working to redesign compute from the ground up. So we at MIM Computing, we leverage a sort of general framework for systems with memory and compute together. But there's some other figures in this space you may have heard of. Neuromorphic computing takes its motivation from the brain, typically spiking neural networks. Then there's Ising machines. Principal approach problems from the direction of Ising model. Quantum computing, which is probably the most famous of these, it endeavors to make aspects of quantum physics accessible for useful computation. And so what's driving these in society today? Of course, we have big technological forces, which essentially are there's a gap between Moore's law coming to an end and the scale of things that we're doing in society. So that means demand for lower energy compute, faster, solving problems that are currently intractable. it's kind of the driving forces. So what is MIM computing? Well, MIM computing is fundamentally, it's a new approach to computation. This diagram at the top right is meant to indicate that complete departure from the Turing paradigm. And it's a model of computation in the scientific sense. So where storage and compute are combined, even in the smallest elements. And MIM computing has useful properties for optimization. For example, it's like a non-perturbative and massively parallel approach. And it gives you the possibility to have problem-targeted architecture for the problem that you want to solve. So how do you go from kind of an abstract computer science model to building something in the real world? So how do you realize one of these? Well, we build around a certain building block called a self-organizing logic gate, SOLG. So these are electronic components. You can build them using standard CMOS elements. Here it looks like a standard Boolean logic gate. And in fact, it is associated with a logical function, just like a standard Boolean logic gate. But this is designed to be a dynamical component. And in a standard gate, you'd have the inputs there at the top leads and the output at the bottom lead. And conceptually, it's a pretty simple device because when the inputs are particular values, you need the output to be a particular value. But in our case, this device has simultaneous input and output at all leads, and it's a little dynamical component. Now, internally at each lead is a dynamic correction module, and its purpose is to interact with other logic gates to create specific dynamics in a circuit of these gates. And they're designed in a very specialized way. And furthermore, some of the components can be tuned. So that's just the one slide description of these components. And so how does MIM computing optimize? Well, if you have an optimization problem, first you represent it as a circuit, a MIM computing circuit, and there's a direct mapping for that. And the variable values for your problem end up being represented by voltages in the circuit. And the circuit design parameters now should be tuned to the problem to solve. And then you can initialize the voltages, and the behavior that you've designed into the SLGs is meant to optimize those variable values for your problem. So here we have what looks like a schematic of a circuit with a bunch of normal gates, but this is a completely different approach. So you see the MIM computing circuit there. I have some indicators showing that you could have the input to the problem be some parts of the circuit, output other parts. It's not that the inputs are where you'd expect on logical gates, probably at the top in this circuit, and outputs at the bottom. So contrast that with the standard approach to optimization, where you can use a general purpose computer. You're going to select your favorite algorithms, which may have come from researchers working hard for decades. And then this computer will have discrete steps in essence, right? Clock cycles. And typically you're iteratively reducing the search space for your problem. So at the end of the day, MIM computing is just a completely different approach to try to solve problems. Great, so even early on, the founders of the company did simulations of this software, and just this new approach was already showing success. For example, an early paper look at benchmark problems, a well-known set, and you give the solver some timeout. I'm now looking at the bar plot at the top right. It doesn't really matter what the timeout is, whether it's 300 seconds or an hour. In either case, MEMCPU, the MIM computing solver at that time, solved more problems to a better objective than did the one that they compared against, which was the best-in-class commercial solver. And didn't really matter what the timeout was. We have a number of papers where you've tested and checked out this approach to solving optimization problems. I picked one more example here where it's computing the ground state of certain Ising models, and you can see that the y-axis is essentially mapped to time, And so lower time is better. And this black line here from the MIM computing architecture, it was not only getting lower time, but also it was increasing with the size more slowly, which is yeah, a nice feature. So I won't spend this talk going on all the results, but there's plenty of references for this. Okay, great. So back to the company. We now develop software solutions and hardware solutions. The software solutions typically are when we're simulating the MIM computing architecture. So I'll actually do a demo of this. We have the MEMCPU Platform, which is online, available for access. It's for combinatorial optimization. But we're also working on designing ASICs as well, which are the hardware version of the same thing. So when it's the hardware version for combinatorial optimization, obviously it should be faster because you're not having to simulate the device, you just have the device. But there's other applications too for these ASICs in real-time compute. I think on the next slide, I will describe more about the software, and then the following slide, I'll give just a little bit more about the hardware, just for your information. So on the software side, this MemCPU platform for optimization, typically the workflow is in industry, there's some need, for example, packing or scheduling or operations. And that problem is formulated in mathematics. And so if you know any of these formats, integer linear programming, mixed integer linear programming, quadratic unbounded optimization, and constrained bounded optimization, if you know those terms, then we're speaking the same language on this. And you can send those via API or web interface to our platform. Give it a particular time limit, and it'll return the most optimized solution that it found within that time limit. So that's the software. Then we're also working in the area of developing this hardware. So we have real-time compute at the edge. So the whole idea is that these are lower power and lower latency than what you do on CPU or GPU or FPGA. And we've done projects and have in varying levels of design applications for graphics processing, combinatorial optimization, of course, some neural networks, and certain linear algebra operations, which are useful for 5G comms. So just a couple more slides about the company. The commercial applications that we've looked at and addressed in this company actually span a number of different industries, from oil and gas to transportation logistics, routing, scheduling, and some others. And so many of these areas, we found that MIM computing can be better, even far better than other methods in many cases. And it's interesting, in some of these cases, there's just tremendous opportunity to optimize because they're essentially not optimizing today. They're using something like a first come, first serve or other practical operational approach, which doesn't explore the possibilities to save people time and money and I mean, kilotons of carbon dioxide. And then in other problems that we've looked at, they are doing essentially their sophisticated optimization methods. And then it's fun because then you get to compare head to head. And so then when you can show a big improvement on those cases, that's a lot of fun. And so we love when we can find that. So not only industry, but government as well. We've done SBIRs with NASA, US Air Force, Space Comm, and Special Operations Command. And we're registered on ABMS. So yeah, so we if you have an important problem, consider reaching out to us because we'd love to be involved. So, okay, great. That was as typical in the DISA-TIM format, a little bit about the company. So now I get to do a little bit of a deeper technical dive because I need to describe part of the core of the technology so you can kind of understand and interpret the factorization results. And this was a report on factorization study from an SBIR we did with the US Air Force. So, so let's start from somewhere familiar as we kind of look down at the nuts and bolts of MIM computing. So this is a standard Boolean logic gate. This is not a self-organizing logic gate. There's a voltage at the leads, of course, and if the voltage is above a logical threshold, then it could be a 1, or if below, a 0. And the component's conceptually quite simple. It's enforcing that the output bit follows a given truth table given the input bit. And notably, the information flows from input to output. And if you have a standard digital logic circuit combining these into a network, obviously inputs flow towards the outputs. So in a determined function. Okay, so that's a familiar case. So these self-organizing logic gates are low dynamical components, and the gate's still associated with logical function, like an AND gate, but its purpose is to remain stable when satisfied, and otherwise contribute to certain dynamics in the circuit when it's unsatisfied. So it can take simultaneous input and output at all the terminals. These diagrams just show a schematic of the voltage, the function of time when they're plugged into the circuit. And you put these into the network and you initialize the voltages randomly and they interact. So unlike conventional logic circuit, this has multi-way information flow. And your input variables can be embedded in the network, your output variables also. So the circuit really no longer represents an algorithm, but it represents a question. And the physical dynamics created by the SOLGs in the network are designed to flow to the answer. So how does that happen? So let's zoom in kind of a detailed view first. One SOLG, one these self-organizing logic gates. And consider, for example, an AND gate that has an unsatisfied condition where you see the input leads have a 1 and a 0, but the output is a 1. Well, the role of the components inside is to correct for this and essentially increase the voltage at the top or decrease the voltage at the bottom so that it can be satisfied, and has particular memory and timescales associated with that. So you can actually interact with the nearby gates and then their neighbors, etc. So the DCMs are specially designed to support this behavior, but they are also tunable because they need to be tuned to generate the correct dynamics to solve problems. So this aspect of tuning is I need to explain a bit, and I'll give quite a bit of information on that. So so tuning is adjusting those little tunable circuitry values. And so how do we tune? Well, you can look at a number of indicators, including voltage correlations in the circuit. So here's voltage correlations as a function of lag between the voltage signals. And you can see if you tune and you see no correlations, which is quite common because things are out of balance, then you're not communicating information through the circuit, and these do not work. So you need to find these parameters. This is just one of the indicators of the behaviors we're looking for, where you have these significant correlations. They're extended over time. And also very key is that they're symmetric in time, which indicates that information is flowing not just one direction to the other, but unbalanced. So, it can be worked to tune these design parameters. So we vary the gate design parameters while you're checking the circuit for proper dynamics and convergence to the solution, if you can. And so that can be a time-intensive step, but we've developed custom CAD tools to accelerate this search. The search is often, we're typically working in more than 100 dimensions these days in this structured landscape often. Notice these 100 dimensions does not depend on the problem size. It's just the freedom that we give to the tuned parts of our DCMs, the dynamic correction modules, and other circuit design parameters actually. And then after tuning the problem, then luckily you've invested that time, but you then can use the parameters on other problems with the same structure. So great. So now on the subject of scaling with problem size. So there's a certain characteristic behavior that you typically see in these systems, which underlies a lot of our practical success. And you can see this, the MEMCPU time to solution typically grows slowly with the input size. And so just a matter of empirical observation that leads to a large speed up when you have large problems. And this is the nice case. This plot came from a work we did with one of the leading oil and gas companies, and just kept going out to the total number of goods that they had. You can see the slow increase in time to solution. So yeah, that's great. Now, there can be a slight complication, which is if you're looking at the scaling of the problem size and you're actually changing the structure of the problem as you increase the size, well, you have to take that into account. So problems that grow non-uniformly, for example, the number of gates doesn't scale the same way for different parts of the circuit. What we're seeing, and it makes sense, is that you have to rebalance your parameters and tune it each different size because they have the different structures. And what we typically see is then you can continue pushing out that scaling to the new sizes. Okay, great. So those were kind of the preliminaries. Now I get to talk about the actual problem of prime factorization. So this might be something that many people are already familiar with, but so RSA 1024 and 2048 modern encryption methods, where those numbers indicate the number of bits of the public keys. And the idea is you have these large prime numbers, you multiply them together to create a public key, and it's hard to go back the other way because it's like a one-way function. So that public key is nice. You can pass it in the open, and someone, like here in this, we have Alice passes it in the open. Bob can then use it and encrypt the message, pass the encrypted message back, and the private key is the only thing that would decrypt it. So prime factorization, of course, breaks this key into the two original prime numbers, yielding the private key from the public key. So, and of course, it's a famous problem. There's a really nice paper from 2010, Impolsky. He made this table. Actually, I've adapted the table and updated it with the most current numbers that I found. But for general factorization approaches to factorize general numbers, he divides it into general and alternative. So up top, you can see of course, the sieve methods. Those are the current record right now for like a biprime factorized is from the general number field sieve, 829 bits. I believe it was done in 2020 and took something like 2,700 compute years. So the known methods have super-polynomial scaling, so they have the records, but it's quite well understood that reaching 2048 bits is not tractable. And so these the other methods, which the paper puts in as alternative, they lag, of course, by far. Shor is definitely notable as a polynomial time algorithm. I'm sure everybody's familiar. Interestingly, and one that I don't know much about, but I wanted to point out, is these twinkle and twirl hardware proposed by Shamir, which is a hardware device that's been proposed, which would be able to do presumably larger than the general number field sieve, depending on how much effort you invest into the compute. But that's theoretical. So another fun plot is the history of RSA numbers factorization. When the RSA numbers challenge, of course, has a list of difficult numbers to factorize by primes. And in the early 90s, this was in the above 300 bits to 400 bits. And you can see the line tracks the record for the largest factorized. Currently, the record stands at 20 from 2020. Those are, and yeah, so you can see it's slowing down this trend. And you can think, well, the progress was partly due to Moore's law and increasing capabilities, which is partly true. But there's other aspects, and one of those aspects is in the blue here, and it shows approximately how many core years were required to actually perform that factorization. And you can see that's also been going up on this exponential scale. So, part of it is we were just willing to invest more compute time into those. So great. Modern records are held by general number field sieve. These sieve methods are held the records for this whole time. And how does sieve methods work? Well, I won't go through all the modular arithmetic and analysis. However, you're finding congruences between integers of specific properties, specifically subject to this property called B smoothness for for the integers. So with a sufficient number of congruences of low B smoothness, then you can efficiently factorize. So sieve methods leverage that just finding the congruences is the bottleneck, and then you can factorize. So for a basis with M primes, you need exactly M plus 1 to be sure that you can then factorize. So during the SBIR, I did many things, but one was used MEM computing for sieving. Now, a MEM computing platform solves integer linear programming problems, which the reason that it was developed this way is because industry uses ILP problems for a lot of its work. So we want to be applicable to industrial problems. This is the most basic description for what an ILP formulation is. Linear inequalities between integer variables. And so during the SBIR, did quite a bit of effort, but I developed this ILP formulation that works well on MEM computing. And the core aspect really to enforce the smoothness is that you can express your integer as a product of integers that have as a limit the largest prime factor that's permitted. So we designed and modeled the corresponding circuit. So here's a layout. Along the X is the different variables. These would be lines that run vertically in the circuit, and along the rows here are the different logic gates which correspond to clauses in the formulation. And so you can see at the top we have bitwise binary products. Probably I should have mentioned that to handle an ILP, this problem of congruences, you do have to take care of other things, including expanding integers and their binary representation, and then taking care of bitwise products. So that's where these top gates are coming from. They're bitwise products in the formulation. And then these bottom gates here are sum gates, which are written in a general form, but they have the same structure as on the previous slide for performing this congruence finding. So, and there's other an important other development that we created was that, so the sieving actually has an excellent pairing with the circuit's design of random initial conditions, which means that you run this circuit and find a solution, just restart it, find another solution, and you just end up streaming these solutions out from the dynamical system. So now the product gates actually grow like n squared, and the sum gates grow as n. So it's a lot of work to greatly improve the CAD tool. So now we have better CAD tool for tuning, and we tune to each size, ran and analyzed the time to compute the congruences as you run the circuit. So we were very curious to, okay, are we going to get this characteristic behavior that we've seen before from MEM computing? And you just do the timings. We tuned on several problems up to 150 bits and tested on a suite of 50 problems generated by the RSA procedure. So MEM computing found congruences all the way up to actually 300 bits. And the time to find congruences is giving a factorization in 6 hours. Now, so for maybe semi-experts, the B smoothness was chose to be to the 27th. So yeah, this requires the pi b plus 1 congruences. And let's see, let me explain this plot now on the left. So right now I've jumped exactly to the yellow and the blue points, which are the circles and the squares. MEM computing run either on the CPU or on the GPU. Those are the simulations of the circuit. And the GPU has better scaling because over this range of sizes, you can easily distribute it over all the cores. And that's what, so now we've, probably these dashed lines are catching the eye. They're just, if you insist on fitting in a polynomial, which you get degree 2 for the yellow line, degree blue, the blue line has degree 4. We wanted to also see, as I have on the next slide, so the, so if you run the same ILP problem with state-of-the-art conventional ILP solvers, and you insist again on fitting a polynomial degree 20. This, actually there's a timeout at the top where we didn't run long enough to see, get a really full scaling understanding of the leading ILP solver. Okay, so, but the timing from MSieve, which is the general number field sieve package, yeah, shows the ideal scaling here, where you do have the super polynomial scaling here. I don't quite get to the crossover. And okay, so that's interesting, right? Get to 300 bits. That was actually, yeah. So that was, we were proud of that. And now continuing further is going to require to tune to extend that range. So now we the idea is you tune, you keep pushing out along the same trend here. We've seen that in the past. We see that even on this project in the past. And so the question that we get is, okay, well, where does this extrapolate to? So you can say also, I guess we can say where it extrapolates to for the simulation is weeks. Now recall, these are for the software solution. So the hardware solution is faster than simulation, and the forecast is 1,000,000 times faster because you're not simulating it, you actually have the hardware. So you just map down to these green points here. And those can currently obtain congruences were actually then already, if they were done on the ASIC forecast, would have been done faster than the GNFS, which of course was just on one laptop core, but okay. So, and if you extrapolate this timing trend, you get enough congruences for 2048 bits in a week for the software, and incredibly fast for the hardware. So again, extending the scaling to those values requires tuning the design parameters for even larger problems. And so that's definitely a step of effort and work that has not done yet. Great. So, but we don't see technical roadblocks for doing that. It seems to be just more of the same as far as we understand it right now. Probably a big scale up in effort, but okay. So now I can show a demo because it seems that we're on time. Let's see. So now hopefully everybody's seeing the login screen. And give me 1 second. Great. So this is when you've logged in to our platform, you can use this platform for, like we said, all sorts of optimization problems. Here are jobs that I've run in the past. I'm going to, for this demo, create a job. I call it, factorization 100, just like the test I did earlier this morning. And going to, okay, so I've just pulled out, let's see, 4 problems of 100 bits. You can see, if you can see my screen, it's probably a small font, but the number that this would factorize has 30 digits. And there's 4 different problems here, so 4 different factorization problems. Okay, so you just upload those to the, SAS that we have here. there's settings here to run the MIM computing circuit with different features. We don't need any of those. But what we do need is, we perform this tuning during the SBIR, and so we have these design parameters. Now, I will show you, I can open up that file, but let me just get this started running now. We can, trying to think of what would be fun to show for the demo, we decided we'd just do a short run and show congruences. So if I submit the job, I'm thinking, yep, that's everything. So we can run those. Okay, so uploading the files. And I'll show you what it looks like as it's running the circuit. So we have those 4 factorization problems, and we're running that with the system. Actually, right now the computers are, so this is still in the queue. Hopefully they get picked up quickly. Yep, okay, good. And so great. Now, as part of this demo, we will then download the results, and I can show you the rate at which we were getting them, the statistics of them. I essentially show that you can complete the full factorization. On this demo, we'll just get a small number of the congruences, just because I'll do it in just a couple minutes. And I guess in the meantime, I can show the design parameters, which, so these are the design parameters which are found during tuning. They've all been normalized so that the values near unity. But in this case, there's 110 of them. They're repeated 8 times, but that's actually just because the format is more general than we need for this. So that is the design parameters that we uploaded and are now running here. And if you click on our SAS, you can see the progress of the job. You can see what your settings were. Let's see if sim time I used 100 sim time. Okay, so that's why it's taking longer. Okay, and I'll demonstrate how you can download the results. Okay, so 1 is finished, 2 is finished, 3 is finished. Any second now. Okay, 4 is finished. Okay, good job. And soon, so now it's uploading the files to the central database so I can download them. And I think actually in the meantime, I can start the new job. Actually, start the new job. And so that was for 100 bits. I'll show the results that came out, but in the meantime, let me go ahead and do the same, but for the 200-bit problem. Again, these are just 4 biprimes. They're 61 or 60 digits long, if you can see those small numbers there. And 100 sim time. Don't need to validate optional files. So just use the same design parameters because there's not 2 different sizes. Submit the job. Okay. Okay, so now so this is the 100 problem, this is the 200 problem. I'll go ahead and download the results to my computer so I can analyze them. Get that over here. Bring my window to this screen. Okay, so download the results. Here they are. Is that the number? 14857. Okay. 7-zip extract. And extract these guys. And then over in the analysis script that we have to see what the rate of congruence is, their statistical properties, etc. I can, and they will check for the B smoothness and factorize. Well, we'll check for the B smoothness and the 6 properties of those congruences. So back to the software platform. You can see this is actually the 200-bit factorization problem it's running. I called it 100, but I should have called it 200. I can change that after the fact. We've tried to make a nice user interface on all of this. And then I'll download those results and we can view those. And in the meantime, while the script is running, I can jump back to the presentation to explain better. Okay, so let's. Okay, so the script right now is analyzing these congruences. It's going to pop up these windows that look like this. And what these show is that, okay, these top 4 for the 100-bit problems, these bottom 4 for 200-bit problems. I list for these displays, we just list the number of congruences that it's found, and you can see the distribution of the smoothness of all of those. Now, keeping the B smoothness fixed, it gets harder and harder to find congruences in general as you go to bigger problems. So, but you just need the same number to complete the factorization. So with this 2 times increase in bits, then what we're looking at is there a 4 times increase in the sieve time, which corresponds to the plots that I showed a couple minutes ago. And so yeah, if you take these, the average, for example, is 2,266. Here, the average found was 569 within the same sim time. And it turns out the same computation time. I'll show you that part in a second. The ratio turns out to be 4, which follows exactly that rate of finding congruences that I demonstrated before. So let's jump back to here, and I'll show you have timings, for example. Also, there's a lot of analysis information that we provide with each run, which are in files and you can download. You can also see here that the runtime here was 1 minute and 22 seconds for this 200-bit problem. And if we go back to a 100-bit problem, the runtime was on that GPU, 1 minute and 22 seconds. So essentially the times are essentially the same. And it's just, you can see that the rate of the congruences is, even in the short term, you can see that that rate going up. Okay, so let me go ahead and wrap up so we can have some time for discussion, etc. MemComputing is an excellent tool for broad range of combinatorial optimizations. It can also be used as an ASIC for fast and low power compute. It's well suited for a sieve approach to prime factorization. And after tuning for problems from 60 to 150 bits, we're finding congruences for up to 300 bits. And that time to solution is increasing slowly with the problem size. So if you insists on fitting a polynomial. It's decreed to polynomial, and it looks like a quite nice fit. The shift in the problem structure size means you have to keep retuning, and that's going to require upgraded CAD tool and substantial compute effort. But extrapolating these trends points to the ASIC getting enough congruences factorized 2048s extremely quickly. Okay, so I'm going to end there. So thank you very much. Please reach out to us if you're interested in any of the services or talking to us in general.
There is a question. Somebody has their hand up. If you guys want to answer that over.
Give me one moment. Let me see if I can.
Yeah, I raised my hand. I don't know if I can ask the question. So.
Sure. Yes. Sorry. No, I'm seeing. Thank you.
So my first question is about the tuning process. Can it be bootstrapped? So you use a smaller MEM computing circuit to tune a larger one, because otherwise you are likely to be limited by the classical methods, right?
I don't know about the second part of your question. The first part is really interesting. It's been referred to as meta MEM computing by by some folks. And if you can use bootstrap MEM computing to do MEM computing, not something that I know much about. And the second half of the question is if it is therefore limited by conventional methods, and it would be true tuning we generally we're using right now, like a Monte Carlo search method. And that doesn't necessarily mean it has the same limits as when you're solving problems in different ways. That's what I would say.
Okay.
Thank you.
If there are any other questions from the audience members, please feel free to unmute and ask at this point in time.
I have another question about the curves for MEM computing on CPU and GPU. No, they seem to be diverging, and no, asymptotically that cannot be true, right?
You're right. Absolutely. So over this range, we see the scaling is better on GPU because you're distributing so well to the GPU cores. Now, once your problem gets big enough that you're saturated in GPU, then you should actually expect it to curve up to be more like the CPU. That actually can be quite a wise way because these problems are not very large, but also depends on the architecture. So, right now we're running on the NVIDIA V100 GPUs, which are very large, but there's already the A100, which factor of 2 in cores, so the architectures are progressing. So we just kept it with the GPU scaling, and because the problems are small. So I don't actually know where to draw exactly the curve to the CPU scaling.
Okay, thank you very much for your answers and for our presentation.
Oh yeah, thank you.
Any other questions from the audience members? Please ask at this point in time.
I have a question. Can you compare MEM computing approach with analog set approach? So these are basically quite similar cases, right? So it's dynamics of large size classical systems. And in analog set, last year they demonstrated an ASIC that shows transition to the chaotic behavior in the case of complex problems. Can you give any comments about these results and differences in MEM computing?
Yeah, you're saying you're asking about similarities between Eisen machines and MEM computing.
No, I'm talking about analog set, the approach developed by Zoltan Toroskaya.
Oh, said. Okay, I am afraid I'm not familiar with that one. So we have the technical lead actually. Shirley knows because he's been more involved in this space. So I'm sorry, but I don't think I know that platform.
Like I can drop a link probably.
Yes, that would be great. Thank you.
There was a question in the chat area. I'll read it to you. If there aren't any questions on this subject, can you share your vision with MEMCPU RT-NN?
Oh, yes. Okay, yeah. So that is a project on the hardware, which I was not involved in. However, yeah, there's a couple of aspects which you can do much. You can do very well in the computing related to neural nets. One aspect of that is training, where we have results showing that in fewer epochs you can get higher accuracy than with the methods we compared against. And as far as this chip, because I wasn't involved in that, I'm going to probably have to point it to our business folks or our product page, but please don't hesitate to reach out if you're interested. We do have also on the website, you can just download different material that we've described some of these projects with. I believe we have one for that chip as well.
Okay, great. Thank you. If you can post up the slide that has your contact information, that would be greatly appreciated at this point in time.
Yes.
I would like to close things out by thanking MEM Computing for coming in today and participating in this excellent presentation and demonstration to our audience. We thank you so much for that. I'd like to thank those in the audience for taking time out of your day to participate in this session. And a question just popped up in the chat area, and I'll read it to you. How long does the obtaining the tuning parameters for the 100 to 200 bit factoring sizes take?
Yeah, that's a great question. I don't have a number. We could ask the tech lead from this project. Part of the thing is because we were developing this at the same time as we were doing tuning, and things were kind of in time, happening at the same time. I'm not even sure if we have a precise number for you. I can give possibly an estimate. I probably shouldn't give an estimate because maybe I'll be wrong. So. But generally, this was done over the course of probably a few days of a few cloud compute VMs CPU for a particular size, like 100. That's my guess. So, but please know that's just a guess.
Okay, great. Thank you. All right. If you're interested in reaching out to the company for further discussions, further exploration of the technology, the contact information for the company is on the screen right now. If you don't feel comfortable reaching out to the company directly, you can contact my organization, this Emerging Technology Directorate, and we can intercede in discussions on your behalf. I also like to put a plug in for our DISAWorks Innovation Lab located in Columbia, Maryland. We hold these technical exchange sessions in conjunction with DISAWorks. DISAWorks is our lab space to perform testing, evaluation, piloting of technologies that are out in industry, look for potential incorporation within the DISA and DoD infrastructure. So if you are interested in looking at this technology or any other technologies out there within our lab space, please reach out to my organization for further discussions. So again, thanks all of you for your time and taking part in this session. Wish you all a wonderful day. Take care.
Yes, thank you. Thank you.